Okay, so now I'm going to talk about what are called composition methods. And so the idea, if you will, behind composition methods involves taking underlying one-step method and then taking different time steps of it and then taking its composition and doing this in such a way that you end up getting a method which has effectively higher order of accuracy. Okay, so let's say you have psi h be a sort of one-step method. Right, and then you have gamma 1 to gamma s be real numbers. Okay, then we say that its composition with step sizes gamma 1h to gamma sh, right, is the following. So you compose, it's like this underlying one-step method with a whole bunch of different time steps, gamma 1h all the way up to gamma sh, and then you get a new method which we call a composition method. So this is the corresponding composition method. Right. So so let me state a theorem. It's like about the order of accuracy of the composition method, given some knowledge, if you will, of the order of the underlying one-step method, and more or less it has to do with essentially, taking the the leading order error. It's like term, it's in the one-step method, but now with different time steps, and then seeing whether or not, if you choose these time steps wisely, whether those terms cancel. Okay, so that's more or less where the this theorem we have, it's like comes from. So the theorem is as follows: that if you have a one-step method of order p, okay, and then if you consider the following type of composition, right? So you want to basically impose conditions on the gamma 1 to gamma s. So you need that the sum of the gamma 1 of the gamma i's from I equals 1 to s, it's like is equal to 1. Okay, that's perhaps fairly reasonable. It's like, you want the total step length, it's like you've taken, it's like you've marched the solution forward to be h. It's like so you want to get a method like that. And then the other condition is that the sum from I equals 1 to s of gamma to the I p plus 1 is equal to 0. Okay, and then this condition, again, it's like just comes from the fact that if you look at the leading order error terms, and then when you take the composition, you have to basically multiply, it's like these errors together. Then it's like when you look at the errors again, it's like you'll see that the sort of the leading order error term in the composition, it's like involves this as a factor. Okay, and so if you set that it's like sum, it's like to 0, then that means that that leading order error term, which is the same order as the underlying one-step method, vanishes, and then you get a method which is actually one higher order. Okay, so if you satisfy this condition, then the composition method is at least of order p plus 1. Okay, so that's kind of nice. So let me sort of just make some remarks so you can ask, it's like under what circumstances it's like you can actually find solutions, or you can find sequence of substeps, if you will, gamma 1 to gamma s, it's like which satisfy those kind of conditions. So let's look at some examples. All right, so this system of constraints, if you will, on the gamma 1 to gamma s's has no real solution if p is odd. Okay. All right, so that's just an observation, and more or less it's like you can sort of see this because this condition is that the sum of the gamma i's is equal to 1, which basically means that at least one of these things has to be non-negative. But the second condition is that the sum of gamma I to the p plus 1, right, is 0. Okay, but if p is odd, then it's like p plus 1 is even, and so you know, when you square and when you take any real number to an even power, right, it's going to be a positive, or at least a non-negative number, and it's only 0 if that number is 0. But you've already established from the first condition that at least one of the terms is non-zero, right? So you can't possibly satisfy this second condition in light of the fact that the first condition implies at least one of the gamma i's is not 0, again when p is equal to odd, right? P is odd. Okay, so it's easy to convince yourself that this system of equations, again, has no real solutions if p is odd. Okay, so the other thing is that the smallest s and s is, of course, the number of sort of substeps you have to take, the smallest s, which allows a solution, is s equals to 3. Okay, so if so it's perhaps not so you know, unusual then to impose some sort of symmetry condition that you know, maybe it's gamma 1 is equal to gamma 3. It's like for the s equals to 3 case. So if we impose the symmetry condition, which is that gamma 1 is equal to gamma 3, right, then we obtain some values for gamma 1, gamma 2, and gamma 3. So let's just write this here. So I'm running out of space. Okay, so we obtain the following. Let's just call that star star, right, which is that gamma 1 is equal to gamma 3 is equal to 1 over 2 minus 2 to the 1 over p plus 1. Okay, and then gamma 2 is equal to minus 2 to the 1 over p plus 1 divided by 2 minus 2 to the 1 over p plus 1. Okay, all right, so so this particular kind of composition method is oftentimes referred to as the Yoshida composition method. So this is sort of often referred to as the Yoshida composition. Okay, and so if you start with a second order method, then we may apply sort of Yoshida to get a method of order 3. Okay, just erase the theorem. Actually, it turns out that it's going to be order 4. Actually, I should say for a symmetric second order method. So this is when it's most widely used, is that you start with a symmetric second order method, you apply this Yoshida composition method, and then by this theorem which we stated, the method is guaranteed to be at least one higher order, so it's guaranteed to be order 3. But because of the fact that you have the gamma 1 is equal to gamma 3, and the underlying one-step method, the underlying second-order method, is also symmetric, then it turns out that this palindromic composition, if you will, of a symmetric method is again symmetric. Okay, so so because gamma 1 is equal to gamma 3, right, this composition of a symmetric method is symmetric. Okay, and then now we know that if you have a symmetric method, the order of accuracy has to be even. Okay, so we've proved that the order of accuracy is at least 3 from this composition theorem we established, but because this composition of symmetric methods has this palindromic property that gamma 1 is equal to gamma 3, right, then that is again a symmetric method, so it has to be at least even order. So that actually means that this Yoshida composition of a symmetric second order method is actually order 4. Okay, so so this implies that the Yoshida composition of a symmetric second order accurate method is order 4. And the nice thing is that then you can repeatedly apply this argument to keep increasing the order by 2 each time. Okay, so one may then repeatedly basically apply Yoshida composition to get sort of order 6, 8, and so on, right? So sort of increasingly higher order. So that's kind of interesting. All right. All right. So you might ask, it's like, well, is there something you can do with composition methods where you're no longer restricted to the case where P is even? And as it turns out, it's like what you can do is that you can do compositions not just with the underlying method, but with its adjoint. And then if you recall, it's like we had this theorem which said something about the leading order error term of the adjoint method in terms of the leading order error term of the original method. And then there's this 1 minus 1 to the P power. It's like in that coefficient, and you can then take advantage of that to, you know, it's like to rewrite. It's like the constraints. It's like which the gamma 1 to gamma s, you know, satisfies, and this sort of, you know, revised version of the constraint equations in order to get higher order then has solutions even if P is, even as real solutions if P is odd. Okay, so so let's look at that next.